Yes, ladies and gentlemen, you're welcome once again to this yet new another subtopic under modern physics. And today we're going to be looking at radioactive decay processes. Remember, in the previous lessons, we looked at radioactivity. Do you remember its definition? Can you say it out loud? 1 minute. Okay, yes. We said that radioactivity is the spontaneous disintegration of an unstable radioactive nuclei with emission of radiations and energy. That is how we defined radioactivity. Still, we looked at describing the structure of an atom, in other words, in terms of the atomic mass and the atomic number. In this lesson, we're going to be looking at all of those. So let's begin with radioactive decay processes. Now, the objectives of this lesson are basically a few of them. There are 3 or 4. Number 1 is that every one of us must be able to state the types of the decay processes, that is the alpha, beta, and gamma decay processes. Then we must be able to state the rules that we follow while writing the nuclear decay equations. And then finally, to write balanced decay equations. All right, let's begin. Nuclear decay processes. How many are they? I've just mentioned about them. Yes, there are 3. We have the alpha decay process, we have the beta decay process, and the gamma decay process. Now, during the alpha decay, always the alpha particles are released. It can be 1, it can be 3, it can be as many as possible. Alpha particles are always released during that decay process. During the beta decay process, beta particles are always released as well. And during the gamma decay process, only gamma rays or the energy is released. Now, during the alpha and the beta decay processes, always energy is also released in addition to those 2. And we're going to be looking at equations of all of these, but you need to know that in any particular question, in any particular decay process, we can have only alpha particles emitted, or beta particles only emitted, or gamma rays only emitted. Or we can even have a combination of all the 3 or 2 of them, all released in one decay process. So, before we start on that, what do we need to know about this? The rules that we follow while writing these decay processes are basically 2, and the first one is concerning the atomic mass. Do you remember another name for atomic mass? Yes, what is it? Yes, we say that atomic mass is the same as the mass number, or it is the same as the nuclide number. The nuclide is the combination of protons and neutrons. So the total atomic mass before the decay process is always equal to the total atomic mass after the decay process. In other words, on either sides of the equation, the atomic mass this way must be equal to the atomic mass this way. So in case we have 2 nuclides or 4 nuclides or whatever number, you always first of all have to add all of them, and then they must balance with those on the right hand side as well. The same applies to the atomic number. What is another name from atomic number? Yes, it is the number of protons, or the proton number. So likewise, the atomic number on the left-hand side must be equal to the atomic number on the right-hand side. I mean the sum. You add up all of those, whether they are 2 nuclides X, Y, Z, or whether they are any given number, always add all of them, and they must be equated to those on the right-hand side of the arrow, all after the decay process. So, with that brief introduction, let's try to look at each of them in details, beginning with the alpha decay. What is an alpha decay? An alpha decay is one where an alpha particle is given off during the decay process. It can be 1 alpha particle, or it can be 2 of them, or it can be any number. So, remember that an alpha particle consists of 2 protons and 2 neutrons in the nucleus of an atom. So, once they are emitted from an isotope, the atomic mass and atomic number of the parent isotope, in other words, the one that is before the decay, always changes by 2 and by 4 as the atomic number. In other words, what I'm saying is this, that for example, if this is our parent nuclide X to our new nuclide Y, since these ones have been released from the nucleus, it means that the number of protons reduces by 2, and the number of the atomic mass also reduces by 4. This is what I mean. That when a nuclide undergoes an alpha decay, it loses 2 protons and 2 neutrons. It means therefore that the mass number reduces by 4. We're going to see this, and its atomic number reduces by 2. Now, from the periodic table, you know that the position of the element in the periodic table is determined by the number of protons. So if the number of protons, the atomic number reduces by 2, it means that that nuclide, the daughter nuclide, the one which is formed after the decay process, that element will always be 2 steps before or 2 steps to the left in the periodic table, because it has lost the parent one, the parent nuclide has lost 2 protons. Now let's have an example here that given a reductive element X which undergoes an alpha decay to form another element Y, the nuclear equation for this process is given by this. In other words, on the left hand side we have only one nuclide, which is X. We call this one the parent nuclide. So it is having an atomic mass A and atomic number Z. Now once this one gives off an alpha particle, this is the alpha particle. We can represent it like this, or we can even represent it as this, 4, 2, like that. So during these processes, you need to remember how to represent an alpha particle, a beta particle, and a gamma ray. How to represent them. In case you have forgotten those, then you'll be finding challenges here, but it is simple. So if it gives off only one alpha particle, this is one alpha particle, then it means that for the daughter nuclide Y, the atomic mass reduces by 4. That's why we're subtracting here by 4. And the atomic number reduces by 2. And that is an equation for an alpha decay. And always energy is released in any of the decay processes. So that is what we mean by an alpha decay. Let's have examples here. An example is that the decay of uranium 238 is given by this process here to another nuclide, thorium, TH. You don't have to cram these names here. Just mind about the letters that are written here. So that nuclide U, which is the uranium 238, decays, giving off one alpha particle to another nuclide, thorium, which is TH. Now, explaining this one more, I can simply say that on the left-hand side, the atomic mass is 238, and then on the right-hand side, the atomic mass is equal to 34 plus 4, which must also be equal to 238. So in other words, the atomic mass must balance on both sides. Likewise, the atomic number on the left-hand side is equal to 92, and on the right-hand side, it is equal to 90 plus 2, which gives us 92. So in case of being given a question whereby this one hasn't been given, you simply use that rule, that 92 on the left-hand side must be equal to any figure which is here plus this 2 here. You'll have got the balanced equation. So we note that the mass and atomic numbers must balance on either side of the equation. I've explained that. And an alpha particle can as well be written as a helium nucleus, like that. Not a helium element, but the helium nucleus, because radioactivity occurs in the nucleus of an atom. All right, so let's have another question here. The question says that show the equation for the plutonium 239 Pu decaying by an alpha emission to uranium, atomic number 92. So try to write a nuclear equation. What do we do here? Of course, you begin by saying that we have Pu 239. This one is decaying to give off another daughter nuclide, which is uranium U, with atomic number 92. And they're saying that it decays by giving off one alpha particle. So we simply add one alpha particle and then plus energy like that. Now what we don't have is the atomic number of Pu and the atomic mass of U. So you need to first of all find these values and then write another full equation. So what do we do here? We simply say that for the atomic mass, on the left hand side I have 239, on the right hand side I have y plus 1 times 4, because we have only one alpha particle. So you find the value of y as equal to 239 minus 4 and get the answer as 235. So that is the y. Then you do the same for the x. You say that for A, for the atomic number Z, we have that our x on the left hand side is equal to 92 plus 1 times 2. And this will give us our x equals to 92 plus 2, which gives us 94. So you write another equation whereby you replace these values of x and y, and therefore our equation looks like that. You always add on the word energy plus energy. So that is how we get an equation of such a decay process. That is an alpha decay process. Now, I've represented this one here, but it can as well be 2 alpha particles, 3 alpha particles, 4 alpha particles, like that. Now, if it is 2 alpha particles, this is the same as writing it as 4,2 helium plus 4,2 helium, like that. Now, the problem with splitting them like this is that, for example, if you have 10 of them, you'll be having a long equation. So what you do is simply summarize it and write it in this form. Okay, so we have that question there, another question for you to try out first, then we discuss it after you've tried out. So it is saying that given that a nuclide X239 decays and gives off 10 alpha particles to form another nuclide Y, write a balanced equation for the decay. Pause the video for 2 minutes, 3 minutes, and then you come back and watch the solution. But first try it out. Okay, so in our solution, we shall simply say that we have our nuclide X, which is the parent nuclide, 239, 94, decaying to another nuclide Y, whose values of, I can simply write my M here and N. You can write any other letters, plus 10 alpha particles. We know the alpha particles written as a helium nucleus, then plus energy. So what we need to do here is to find the values of M and N to come up with the balanced equation. Have you done that? Okay. So what we shall do here, we shall simply say that for the atomic mass, we have 239 is equal to M plus 10 times 4. 239 plus M, equals to M plus 40, implying that our M is equal to 239 minus 40. What does this give us? 74. Very good. So simply come back. Let me write this equation up here. That I have my 239 94x. So 29x 239 94x giving us our x is 199. Our y was 74. Y then plus 1042 helium plus the energy. So that is what we have as that equation there. I hope that you got it right. Okay, so beta particles, what are these? A beta particle, say that a beta particle is simply an electron, and that electron is coming from the nucleus, not from the shell or the orbit of the atom. So beta particles consist of high-speed electrons, and they are emitted by isotopes that have too many neutrons. So when one neutron decays into a proton and an electron, the proton remains in the nucleus, but the electron is emitted as a beta particle. In other words, if we have 7 protons in the nucleus of an atom, and one neutron decays, it forms 1 proton and 1 electron. So this electron simply goes away as a beta particle. And since the number of protons has increased, it means that that element in the periodic table shifts to the right. This is what I mean. That when a nuclide undergoes a beta decay, its mass number does not change, because remember, an electron is represented by this. So the mass is 0. So there's no change in the mass number, but the atomic number increases by 1. In other words, the daughter nuclide moves one step to the right in the periodic table. Remember that the number of protons determine the position of the element in the periodic table. So let's have an example here that given that a radioactive element, let me put Az here, X undergoes a beta decay to form an element Y, then the equation that we use is, can you guess the equation? 1 minute. You can write it out on paper. So our equation is this, meaning that as well like we did in the alpha decay, the atomic mass A must be equal to the atomic mass on the right hand side. And then the atomic number Z must be equal to the atomic number on the right as well. So that is a beta decay. This is a beta decay. We can write it like this, or we can simply write it as a beta minus 0, negative 1, like that. So an example is carbon 14 atom decays to form a nitrogen atom like this. So can you try to prove this? For atomic mass, we have 14 equals to 14 plus 0. So the atomic mass has balance. That is good. And then the atomic number, 6 is equal to 7 plus negative 1, which is equal to a 6. So even the atomic number has balance. So that is a balanced equation. So it means therefore that carbon 14 decays to nitrogen 14 plus a beta particle. And the notes that we take here is that a beta particle being negatively charged has an effect on the atomic number of -1. I've explained that the element changes position. The daughter nuclide changes the position. So the beta particle can also be denoted as an E like that. I've also talked about that. So let's have a question here, an example. You can pause and try it out. Show the equation for sodium 25, atomic number 11 decaying by beta emission to magnesium. Try that, pause the video. I'm giving it 2 minutes. Okay, likewise, even this one we simply say that we have sodium 2511 decaying to magnesium whose atomic mass is unknown. I will give it a letter X and then atomic number Y plus 1 beta particle and then plus the energy. So the trouble that we have is to find the value of X and then Y, and then we write our equation with those changed. So we shall simply say here that for A, for the atomic mass, 25 on the left hand side is equal to X plus 1 times 0, which implies that our X is equal to 25. So there is no change in the atomic mass. Likewise, for the atomic number Z, we shall say that 11 is equal to Y plus 1 times negative 1. I'm multiplying this 1 and this 1 here. Otherwise, in case this was 10, I simply multiply by 10 like we did in the alpha decay. So implying therefore that our 11 is equal to Y plus negative 1. Therefore, our Y is equal to 11 plus 1, which gives us a 12. And therefore, our equation becomes like that. So where there is X, I put there my 25. Where there is Y, I put there my 12. And then plus the energy. Remember that you can also represent this as an electron like that. All right. So gamma rays, gamma decay. What do we know about gamma rays is that gamma rays have no mass. So the atomic mass is 0, the atomic number is 0, meaning that when we have a gamma decay process, there is no change in the atomic mass, in the atomic number as well. In other words, a gamma decay is simply an emission of energy, an emission of electromagnetic radiations. And it often occurs when a nucleus has emitted an alpha or a beta particle. So knowing that, an example here is cobalt. When cobalt decays by emitting a gamma ray, there's no change in the atomic mass, so it remains 60. There's no change in the atomic number, it remains 27 as well. And then plus the gamma ray or the energy, like that. So that is about the gamma decay process. Let's try to this question here. It says that both alpha and beta decay causes anisotopes change in the atomic number and therefore the element. Alpha decay also causes a change in the mass number. Let's begin with anisotopes. What happens to the atomic number? What do you think happens? What do you remember happens here? The atomic number increases or decreases by which number? It decreases by 2 and the mass number decreases by 4. How about beta particle? When the beta particle has been emitted, the atomic number increases by 1, correct? And the mass number remains unchanged. For the gamma decay, there is nothing that changes. And then let's try out this question as well. 3 parts A, B, C. Pause the video, try it out. In other words, what is here? What is there? What is there? What is there? What is here? What is here? And then what is here? Okay, I hope that you have done that. So, number part A, atomic mass 59, atomic number 27. For beta particle, -1. Then for part B, the atomic number radian Ra is 88, atomic mass Rn is 220, that is great. We have the 2 because that is an alpha particle. And then for C, the atomic mass of nitrogen, that is N, is 16 because added 16 plus 0. And since we have -1 here and 8, then that means that this is a beta particle. So we have our oxygen. You must be knowing that from chemistry. That was just came as a by the way. And then lastly, we have a beta particle, an electron. So that is good in case you've tried that with that. Let's have some general questions concerning all the 3 decay processes. So an example says that a radioisotope 21684P decays by emission of a beta particle to an element Q, and then element Q decays to an element R by emission of alpha particle. Write the equation for these nuclear equations, for these nuclear reactions. So what we shall say that we're having 2 processes in one. First of all, decays by emission of a beta particle, then decays by emission of an alpha particle. So we have 2 processes in one. So the first thing is that we have to write our 21684P. This one decays to another atom, which is a Q, and then plus a beta decay. I mean plus a beta particle. In other words, an electron. And then plus the energy. So we have to find out what is there and then what is there. So can you guess what is here? Okay, beta particle. So this is 216 because there is no change. You found that that is correct. And then what is here? 85, correct. So that is the first process. Then the next process is that the Q, we've got 21685, decays to another element R by giving off an alpha particle. So we have 42 helium and then plus the energy. So what is here, what is there? As well, using our rules, the atomic mass must be conserved. So we have 216, we have to look for a value which is here to make 216 as well. So 216 minus this, I'll get 212. I hope that you got to that. And then here I have my 83. So that is what we have as far as this is concerned. Alternatively, someone may do this, that we have 21684P decaying to give 21685Q plus a beta particle, which decays again to give off 21283R and then plus 42 helium, then plus the energy. That one is also very okay. In other words, for the 2 arrows, this and this, does the atomic mass, atomic number balance? That is correct. That is okay. Then from this other second arrow, combining these 2, does the atomic number, atomic mass balance? Yes. So someone can also write this as that. That is number 1. Then number 2 says that there's a P here. A symbol NP denotes a neptunium nucleus. What is the meaning of 237? What does it mean? Okay, this is the total number of protons and neutrons in the nucleus of an atom. Don't simply say that it is atomic mass. Give us what that means. It is the total number of protons and neutrons in the nucleus of an atom of neptunium. And then 93 means the total number of protons in the nucleus of that atom there. So that is what those two mean. Then they go ahead and tell us that write down a balanced nuclear equation showing the decay of neptunium to a nuclide Y by emission of 5 alpha particles and 2 beta particles. So I'll simply have my solution as 23793 NP. This one decays to give off another nuclide Y, and then plus 5 alpha particles. So I have my 4,2 helium, and then plus 2 beta particles, 0, -1 E, then plus the energy. So all I have to do is to find out what is missing here and then what is missing there. I will give this one my letter X, this one my letter Y, and I find out the values of this. So what I need to do is to use our rules. Atomic mass. For the atomic mass, they must balance. 237 must be equal to X plus 5 times 4, and then plus 2 times 0, which is the same as 237 equals to X plus, this is 20 plus 0, implying that my X will be equal to 237 minus 20, which gives me 217. And then for the atomic number, I'll simply say that 93 is equal to Y plus 5 times 2 plus 2 times -1. This is the same as 93 equals to Y plus 10 minus 2. 93 is equal to Y plus 8, implying therefore that my Y will be equal to 93 minus 8, which gives me 85. Therefore, my equation will be 237 93 NP, decaying to X is 217, this is 85Y plus 542 helium particles, and then plus 2 beta particles, then plus the energy. That is my equation. Hope that you got that one as well. Lastly, let's try to fill up these spaces by using any of those words there. So when an unstable nucleus emits an alpha particle, its atomic number falls by, what do you think? Yes, by 2, that is correct. And its mass number decreases by, by 4. Then beta particles are emitted by nuclei with too many what? Neutrons. In this case, the atomic number increases by 1, yes, while that dash number remains unchanged. That is the mass number, correct. And lastly, gamma rays consist of electromagnetic radiations that is emitted from the nucleus when it loses, of course, the last word is energy, often after undergoing an alpha or a beta decay. So with this, I come to the end of decay equations, and I hope that you've enjoyed it. And next is for you to do an exercise in the next part. Please invite your friends to join you on this website, and we enjoy together. Have a lovely day.